moment of inertia question for a ring. Let us consider a ring here. Two diametric axes. Let's call it the x and y. This is of mass m and radius r. So the radius of the ring is r and mass is m as given. Consider another axis passing through its center and perpendicular to both these axes. Let's call it the z. We know that the moment of inertia about the z-axis for a ring is mr square. This is what we know about an axis through its center perpendicular to the plane of the ring. For us, this x and y both are diametric lines and therefore are axes of equal status for the moment of this ring about each of these axes. Hence, Ix would be equal to Iy. Moment of inertia about x-axis and about y-axis would be equal. But by perpendicular axis theorem, Ix plus Iy is equal to Iz. That means each of this is equal to mr square by 2. Now see, the surprise in this question is about the diameter r. Now if the diameter is r, that means the radius, let's say if this is the radius, then this radius is equal to r by 2. That means this is going to be equal to mr square and therefore mr square by 4. And that means this is going to be mr square by 2 and hence equal to mr square by 2 means mr square by 8. Half mr square by 8. They are talking about a tangential axis lying in the plane of the ring. Now, if that tangential axis is parallel to the y line, let's say this is the tangent or tangential axis, and it turns about this, then parallel axis theorem would also be needed. And that means the shortest distance between them being the radius, which is equal to r by 2 into the entire mass. That means It, moment of inertia about the tangential axis, would be equal to Iy, moment of inertia about the y-axis, plus the entire mass of the body into the shortest distance squared. So therefore, the moment of inertia about the tangential axis is plus that makes it, I think, like 2 mr square by 8, 2 plus 1, 3, 3 by 8 mr square. And we have the answer. That's it. Simple question involving perpendicular axis theorem and the parallel axis theorem. I would say this is a great question. Thank you for your patience.